Welcome back again to MP Live Lessons. This is Maths Paper 1, GCSE. So this is for the exam board AQA, and I've sifted through the advanced information and taken off a few easy topics that people usually get right each year. And we're focusing on the harder ones that people don't tend to get right in many years. First, we're going to start on stuff covered with both tiers. So we'll start with the Unit 1 number. And as an overview, here are all the topics which you could screenshot right now. And for both tiers, we'll first start with the laws of indices. So when you multiply indices, you need to first add the powers. Suppose, let's say we have the two numbers 2 to the power of 3 times 2 to the power of 8. So I'll be writing out 2 times 2 times 2, so like writing 2 times 3 times. And then the second bit, 2 to the power of 8, is multiplying to 8 times. So if you multiply them all together, you just add the two powers and you get 2 to the power of 11. This only works, as well as some other rules, when the base is the same. So the base is your normal number, and your power or index is here, just the raised bit. The opposite will happen if you divide. So when you divide powers, you'll instead subtract them. This can commonly be seen in a fraction such as 5 to the 8 divided by 5 to the 4. That'll be 5 to the 8 minus 4, which is 5 to the 4. The last rule is raising a power to another, so like in a bracket. For example, if I have 3 to the power of 3, and then we have, let's say, to the power of 4. This is the same as writing out 3 to the 3 times 3 to the 3 times 3 to the 3 times 3 to the 3. So which is really 4 lots of 3. So it's just 3 to the 3 times 4. So you multiply the powers this time. Now, we can use laws of indices, especially in other circumstances, such as commonly standard form, and you'll need to sort of manipulate them perhaps as well. This also works for algebra as well, so for letters. You could try these yourself, such as x to the 6 times x to the 4. And another one you could try is y to the 5 divided by y to the n. So we're just applying the rules again, and we're writing them as a single power of something like x in question 1. So the base stays the same, which will be x, and we just add the powers together since we're multiplying. So the final answer is x to the power of 10. If we're going to write question 2 as a power of y, the base stays the same again, which is y. And since we're dividing, we do the top number minus the bottom number, so 5 minus n. And you just leave it as it is. You may need to know some other information. For example, anything to the power of 0 is 1. And a way to prove this is, for example, 5 to the power of 1 divided by 5 to the power of 1. Because when you subtract, when you divide, you subtract the powers. So you'll get 5 to the power of 0. Another way to write this is also 5 to the 1 is just 5. So 5 divided by 5 is 1. Therefore, 5 to the 0 equals 1. This works for any number really, including letters as well. You also might need to know about fractional indices, though this is more likely to be a higher tier thing. So this is where we use roots. So let's say we have 6 to the power of a third. This denominator becomes the root. For example, this 3 here, we put it outside, we draw a little surd thing, so it becomes a cube root of 6. If the numerator is something different, like let's say 2, you'd put this in brackets, then put whatever is in the numerator here. And just to remember as an order, you need to first root, then raise to the power. You'll also need to know about negative indices. So in this case, I'm going to show you a little pattern. For example, we'll use 5 again. So we have 5 to 5 squared. This is 25. 5 to the power of 1, that's just 5. 5 to the 0, that's just 1 as we know. As we can see, each time we go down a power, we're dividing by 5. So when we go to 5 to the minus 1, we divide by 5 again. We get 1 over 5. 5 to the minus 2, divide by 5 again, you get 1 over 25, and so on. So let's say if we have, we'll use a letter this time, x to the minus 3. What you do is you take the reciprocal. So that's 1 divided by something. So that'll be 1 divided by x, and since you put it in the reciprocal, you turn it around. That's how you write a negative index, or a negative power. Now a good use, as I said before, with powers is standard form, and we write this in the form a to the times 10 to the power n. So n has to be an integer or a whole number. And a needs to be between 1 and 10. As in, it can include 1, but not 10. And for converting, for example, we start with the decimal point here. Every time we shift the decimal point to the left, we are dividing by 10. So to compensate, you'll need to increase the power of 10 by 1. So we always start at 10 to the power of 0. So that's 1, 2, 3, 4, 5, 6, 7. And then 8 as well, because that will be 3.4. So that falls in between 1 and 10. We've moved the decimal point 8 places to the left. That means this is really 8 or 10 to the 8 times smaller than it should be. So this goes as our power. So if it's a large number, we have a positive power. So the final answer is 3.4 times 10 to the 8. So as a reminder, Our next example would be this very small number here. And if we use the rules above, we expect this to have a negative power instead. So we keep moving the decimal point until we get a number that's between 1 and 10. So we'll move it to the right 1, 2, 3, 4. So we get 5.47. Since this is a small number, we have a negative power, 10 to the minus, and that's the number of places we move the decimal point, so 10 to the minus 4. So to recap, if it's a large number, our power would be positive. If it's a very small number, our power would be negative. And the actual number would be how many times we move the decimal point to the left or to the right until we got a number that's between 1 and 10. If you're asked to round, you would round this portion here. Now, calculating the standard form can be a bit hard. So for example, we could be asked to calculate this. What we do first is we remove the brackets. So we'd write them all in one line because multiplying, it doesn't matter how in which order you multiply. So we'd have 2.7 times 10 to the 3 times 4 times 10 to the 5. If you remember from the laws of indices, we could easily collect or multiply together the powers of 10 here and here, and we can just multiply the ordinary numbers on their own, such as the 2.7 here and the 4 here. And what we'd get, so if you rearrange this, you get 2.7 times 4 times 10 to the 3 times 10 to the 5. So at the end we get 10.8 times 10 to the 8. And usually you'd be asked to give your answer in standard form. But this isn't in standard form because this is not between 1 and 10. So really, our number should be 1.08, but we've moved the decimal point to the left once, and that makes it 10 times smaller than it should be, than the last number. So to compensate, we multiply this bit here by 10, so we increase the power by 1, 10 to the 9. Or really, you could say 10.8 is 1.08 times 10 to the 1, and you could just multiply this and the 10 to the 8 together. Another example could be this. It's better probably to write it as a fraction. So this is the numerator on top. So we have 5.8 times 10 to the 3. On the bottom we have 2 times 10 to the 4. And we can highlight each bit again that we can combine together or handle. So the normal numbers like 5.8 and 2, we could just handle easily. And we can deal the powers together here, the 10 to the 3 and 10 to the 4. So we can write this out as two separate fractions. We have 5.8 divided by 2. This is still multiplied because we have these in between. 10 to the 3 divided by 10 to the 4. And what we get is 2.9. So already this number is okay. It's between 1 and 10 times 10 to the 3 minus 4. So 3 minus 4 is a negative 1. So 10 to the negative 1. Next, we have ratios and fractions. So simplest form is where we try and divide the ratio down until we can't get any further. So what I mean is, for example, with a ratio of 30 to 75, we could easily divide both sides let's say 3. So we then get 10 to the power of 10 to 25. This is still not simplified because we could still divide both numbers, this time by 5. Now we get 2 to the 5. So this is fully simplified. Now, with ratios and fractions, you might be given them in a little equation like this, x to y equals 4 to 7. It can be a bit confusing at times to see which one is larger than the other. So there's a trick. What we do is we tie the inside two together and the outside two together like this. And what you do is you simply multiply them. So we can see x times 7, so we get 7x. And it doesn't matter, you should have one side containing x and one side containing y. And then the other side will have 4y, so 4 times y. For example, you could express y in terms of x. This means y on its own. So this would be y equals, and since we divide both sides by 4, we get 7 over 4x. You could also do the opposite, so express x in terms of y. So we have x on its own. To get that, we'll have to divide both sides by 7, so we have 4 over 7y. Next, we have some ratio problems, and I've identified a few that have come up in the past papers and might come again soon. One of them could be scaling up or splitting something. For example, green paint can be made by mixing blue and yellow paint in the ratio 4 to 5. Now, how much are needed of each paint to make 13.5 litres of green paint? So what we're really doing is kind of splitting to see how much of each do we need. So what we have is the ratio 4 to 5, and I like to call each bit in the ratio a part. So 4 plus 5 is 9, so there's 9 parts to share. Then what I do is I see how many liters or how much paint there is per part of green paint, since this is a total. And what we get is 1.5 liters per so-called part. And that's what we multiply each side by. And at the end, we get 6 to 7.5. So that means we need 6 liters of blue paint and 7.5 liters of yellow paint. The second type of question could be combining ratios together. So like you might have two pairs and then one common variable. For example, in a restaurant, the ratio of men to women is 4 to 3. So we'll write that down. So we'll represent the number of men as an M and women as W. Men to women is 4 to 3. And the ratio of women to children is 4 to 5. There are 172 people in total. How many children are there? So what we can do first is make one big ratio involving men to women to children. We can basically, if you like, tie these ratios together because there's women appearing in both, but they're not the same, so we can't exactly combine them easily. So what we do is we multiply them to the same number, such as 12 in this case. So this one will multiply by 3, the other one will multiply by 4. So the ratio of men to women to children, so we have for every 16 men, there are 12 women, and there are 15 children. And what we can do is we can do that same splitting method again. So we find out the number of parts here. And what we get is 43 parts. And we see how many people the parts per people there are, or people per part there is. So 172. And actually, we could try something. We could try 43 times 4. Let's test that out. Okay, perfect. So there are 4 people per part in the ratio. So we multiply each by 4. So what we get at the end is we only need to know the number of children. So we've got 60 children. 15 times 4 is 60. Last one is something enough, right? So we've got, let's say, we want to make salt water for a fish tank. And to make the perfect salt water for our fish, we mix in 3.75 grams of salt for every litre of water. Now, there's 15 grams of salt and 5,500 milliliters of water. Just before we do anything, we need to convert this litre into milliliters. So 1 litre, it's a very easy conversion, is 1,000 milliliters of water. And the question asks, how much salt water can we make to like the maximum? And this is a bit of a trick question because we might have too much salt or too much water if we simply combine them together. So what we have to do is we see how much water we need with this. How much salt we need. So first we need to see how much water we need for this, or how much salt we need for this. You only need to do one comparison. I'm going to see how much water needed to dissolve 15 grams of salt. So for every 3.75 grams of water, we needed 1000 milliliters of water. I've got 15 grams of salt, and we don't know how many milliliters of water this needs. So I'm going to see how much I need to scale this up. I think it's 7.5. So we need to multiply this by 4, therefore this side by 4. Because that's how it works with ratios, to keep each proportion the same. So to dissolve 15 grams of salt, we need 4,000 milliliters of water. That means we have some leftover water. We can't add any more. So actually, the maximum amount of salt water we can make is this. Next, we have inequality notation. So you need to be familiar with the less than, greater than signs. So less than points to the left, greater than points to the right. And you might have some variance or equal to. So what you'd then do is you can either draw a line here or simply a flat line underneath. That's how you might see it written out on paper or letters or just on Word, for example. On a number line, if it's strictly less than, you'll have an open hole. If it's greater than or equal to, you'll have a closed hole. So this kind of represents, like, it includes. So for example, if I want to represent the inequality like this on the number line, if I roughly mark this out, like 2 here and 3 here, since x can be greater than or equal to 2, or 2 is less than or equal to x, since it's or equal to, we'll need to use a closed hole so it can include, let's say, -2 here. And since x is strictly less than 3, it can't equal 3, so we need an open hole. And what we do is just simply join them up together. If it was open-ended, like if we just had x is greater than 5, we'd have, again, an open hole since it can't equal 5. But since it goes in only one direction, we need to have an arrow, so it goes on to infinity. Next foundation, we just have cost and profit. So cost is like to buy what's needed. For example, in a business setting, this could be materials, maintenance, but it doesn't matter. You need to be familiar with different cases. Selling is the selling price, like from, and therefore profit is the selling money, the money that you make from selling minus the cost. The cost, it needs to be quite low, and the selling price needs to be high to maximize profit. Now, it's called a loss if you don't make enough money to offset the cost. So, not sold enough. And we have a little formula for percentage profit, which might be asked on foundation, such as this would be profit divided by the initial cost times 100. So this tells you how much like of the cost if you've got back. For example, if you sell something that's like 2 times as much as you paid to make it, that's 100% profit. So you get back the cost and another 100% if you like. Foundation tier might be asked to have some unit conversions. For example, frying oil is sold in 2 different places, which is ironically now, at the time of recording, is in shortage at different volumes and different prices. So let's say retail, it's £3.60 for 2 litres, which is a typical um like price actually. And let's say at wholesale they sell better, bigger containers, £8 5 pence for a gallon. And let's say we use the approximation 1 gallon is about 4.54 litres. Now, I'll allow you to use a calculator here to figure out which oil is cheaper. So that's where, for example, we'll find the cost per litre of oil. This one's easy. So we have 2 litres of oil and £3.60 for that. So to find the cost per litre, so we do £3.60 divided by how many litres that is for, so 2. That gives us £1.80 per litre. For wholesale, we'll have to convert the gallons first. So we know a gallon is about 4.54 litres. So to find out the cost per litre of oil, that would be £8.5 divided by 4.54, which gets you about 1.773 on your calculator. So when you're dealing with money, round to 2 decimal places. So this would be just £1.77 per litre. So actually this is cheaper per unit. Next, for foundation tier is density. So this is actually a crossover with physics, and this tells you how much packed something is, or how heavy it is per unit of volume. For example, gold is a very dense material. It will still feel quite heavy, even though it could be a very small block. So density is how heavy it is, so that's mass, divided by the volume. And there isn't a standard unit, really. If you're doing science, you'd usually put mass as kilograms and volume as cubic centimeters. But for the unit for density, so you'll have your unit for mass, and you'll have a slash or forward slash sign. This shows it's dividing, and then you'll have your unit of volume. So here you'll have your units for a mass, and here you'll have your unit for volume. For example, if you're given the mass in tons, then the volume in cubic meters, the density is tons per cubic meter. And a bit of information, this could be in a question, I don't know, no one can predict. Things that have a density greater than 1 gram per cubic centimeter will sink. Now, for higher tier, you may have to write recurring decimals as fractions. So I'll ask you this. Convert this fraction to a recurring decimal. So first of all, what you do is the bus stop method. So this is what you divide by. So we'd have 11 on the outside, and then 4 on the inside, and we put a decimal point and loads of zeros to keep 4 the same. So we can see, as a result, we've got this bit that keeps repeating. If we keep dividing, we'll just keep getting 3, 6, 3, 6, and so on. So this bit that's repeating is represented by, or marked by, 2 little dots. So the first dot is the start of the repeating unit, and then the second dot is the end of the repeating unit. So this would be written by 4 of 11 is 0.36 recurring, like this, the 2 dots over both. Now to do the opposite, there could be a fast trick. If you're given, let's say, this number as a fraction, this recurring decimal, this would be 0.42 recurring. If the recurring bit immediately starts after the decimal point, what you can easily do is divide this by, let's say, 9, 99, or 999, or so on. So it depends really on the number of digits that repeat. So you divide by 9 if there's 1 repeating digit. You divide by 99 if there were 2. You'd divide by 999 if there were 3 repeating, and so on. So as a little trick, this would become 42 over 99. And remember, you need to simplify this down. You can divide both sides by 3. So that becomes 14 over 33. The alternative method is the algebra version. So let x is the recurring decimal. And you use this when it says prove. can only use this method here if it says prove. What you first do is you multiply x by power of 10 to get one little bit or chunk of the repeating unit to the left of the decimal point. By what I mean is, in this case, you would multiply by 100, so you'd shift the decimal point 2 places to the right, or make all the digits move to the left 2 times. So you get 42, which is one chunk of this repeating 4-2, but you'd still crucially have this 4-2 recurring, because the 4-2 recurring goes on forever. Underneath you'll just have x on its own, which is 0, but also has a 4-2 recurring section. And the magic happens after you subtract, you get 99x. This is why we have the trick of 999 or 999. And you'd also subtract on this side, so you just get 42. And luckily these two recurring bits will cancel out because they're exactly the same. And to get x on its own, we divide both sides by 99. So we get 42 over 99. Simplify it a similar way, and we still get 14 over 33. There may be some harder variants, such as this, where we see have 3-2 recurring bit, the one that repeats, doesn't start immediately. I'd recommend the let x equal the recurring decimal again method. So step 1 is to bring the repeating unit, or the recurring unit, next to the decimal point. So you multiply it by 10 in this case. So 10x is 5.32 recurring. Step 2 is to multiply again. So you get one chunk to the left of the decimal place. So we multiply it by 100 again, so we get 1000x and 10x. And at the ends we get 990x equals 527. Our fraction is 527 over 990, which can't be simplified. So step 3 was to just subtract. Now for higher tier, they'll have to simplify surds. Now, first of all, why would you just write surds like root of 6 instead of its decimal equivalent? This is because it's more precise or exact. And that root 6 is irrational. You'd have to round off at some point. So for surd rules, for example, we start with adding, subtracting. You can only do this when you have the same root. That's like the number in these square roots. For example, you could have the 2 times the root of 3 plus 5 root 3. This works because you have the same root. This works. This is okay. So we add these together. So we get at the end 7 root 3. However, with let's say root 6 plus 2 root 5, you can't do this because then these two are different. Multiplying and dividing is quite simple, really. You just multiply together what's in the two. So it's, for example, root 6 times root 5 is the same as root 6 times 5, like under the same radical sign. So you get root 30. Dividing works in a similar way, such as root 100 divided by root 20 is the same as root 100 divided by 20, and you get root 5. And the simplest form is where we try and get the surd, like to the point where we can't get any square numbers in. So we try and for example, let's say we have the square root of 48. The largest square root number that goes into this is 16. And using this multiplying dividing rule, this can be made up of root 16 times root 3. And this square number inside will go to a whole number. So the root of 16 is 4. So we get 4 times the root 3. Now, a hard topic for higher T could be rationalizing the denominator, and the purpose is to get the denominator as a whole number. Because when calculators do this, it's much easier to divide by decimal rather than the rational number. So, for example, we could do something like this. That's an easy variation. And we have to multiply by 1 to keep it the same. But this is also the same as doing root 6 divided by root 6. You have this, if you have the same on the top and the bottom, it's multiplying by 1. So what you can suddenly do is if you multiply fractions, you multiply the numerators and you multiply the denominators. On the top you'll get 3 root 6. On the bottom you'll get root 36, which gets you to 3 root 6 divided by 6. This whole number 3 can be simplified with this whole number 6. If we divide both the top and the bottom by 3, we can just get root 6 divided by 2. That's in its simplest form. Something harder could be this. We have to use a bit of algebra, so difference of 2 squares. For example, in this case, we have to multiply by 2 root 3 minus 1 on the top and the bottom. So we end up getting double brackets on the top and the bottom. If we use FOIL to expand them out, And in the end, we get 2 plus 7 root 3 over 11. And we can't simplify any of this down. As some practice, here's one past question. To simplify the third into this form here. So we have the root on the top, and a and b are integers. So we just mean whole numbers by this. So first we can see that root 18 and root 50 can be simplified on their own. The largest square number that can go into 18, or is a factor of 18, is 9. And 18 is 9 times 2, so we get root 9 root 2. This simplifies to 3 root 2, because the square root of 9 is the whole number 3. We could do something similar with the root of 50. The largest square number that goes into here is 25. So we put root 2 because 25 times 2 is 50. And this becomes 5 root 2. So if you rewrite the question, we get 3 root 2 minus 28 divided by 5 root 2. An idea now could be to rationalize this here. So multiply the top and bottom by the square root of 2. So we get, in the end, 3 root 2. So we leave that the same. 28 root 2 divided by 10. And this simplifies a bit to a fraction more or less. And we have to put this into a bit of a fraction as well, over 5. And it happens to be that when we take these away, since they have the same denominator, we still have the denominator 5, but 15 minus 14 is 1, and if it's a 1, we ignore it, so we just get root 2 over 5. That's our final answer. And it happens to be in the same form, so we just have the square root on the top divided by a number. Next is Unit 2, Algebra, which has taken a bit long now. And here's the overview for it. You may want to take a quick screenshot. Now we have linear equations and graphs first, and we write it in the form y is mx plus c, and we see that m is often written as gradient, and c is the y-intercept. And when we plot a graph, we'll have a table of values, so we'll have x and y like this. And you'll have a few values like -2, -1, 0, 1, 2. And to get the value for y, you get the value of x, multiply it by 3, then add 2. So multiply by 3, then add 2. So for example, at 0, y would be 2. At 1, it would increase to 5. And here are your other values. And these would be your coordinates. For example, this would be the point -2, -4. And when you put it onto a little graph, I'm roughly plotting this. You should get a nice line where you could just simply draw like this. Now when you're sketching graphs, It's just you don't need to do this here, but you're looking for important information. So you need to know where it crosses the x-axis. So this is when y is 0, so there's like the ground. And when it crosses the y-axis, this is your y-intercept. And you'll usually need to solve a little equation to find these. Now when we're sketching graphs, as I said, you'll look for intercepts, for example with linear, sketch y equals 3x plus 5. So when it crosses the y-axis, x equals 0, so y would be 5, so that'll be 0.05. When it crosses the x-axis, y equals 0, so we have to substitute this in. And another thing to note is when it crosses the x-axis, it's called a solution or a root. So for example, if I sketch it now, these axes here, I'll roughly plot out the y-intercept at 0, 5 up here, and the x-axis intercept, or the solution, -5/3, so on the left. So this is what the graph could look like. Something like this. Whereas quadratic, you'll need to do all of the above, plus the turning point. So if I draw an example of it, many quadratic graphs would have two roots. So if I do something like this, I'll highlight the roots in yellow. The y-intercept in orange. And then the turning point in green. And you'll find how to find this turning point in a little while. When sketching graphs, this is for higher tier. You'll need to know about the reciprocal graph. And you should know by now that dividing by 0 doesn't work, is something you'd have to just leave. And what you get is a nice curved-like graph. It goes near the axis but never touches. And it almost goes the same in here. And you may need to know as well the exponential graph. And a good thing to know, for example, let's say y equals 2 to the power of x. When x is 0, we get 2 to the power of 0 equals 1. So any exponential graph crosses like the point 0, 1, like here, because anything to the power of 0 is 1. And what you'd see, for example, and you just shoot up very quickly like this. Whereas here, it goes near but never touches the x-axis. Higher tier might have to sketch some trigonometric graphs. For example, y equals sine x. A good way to remember sine x starts at 0, peaks at plus 1 at 90 degrees, minus 1 at 270. So you get something like this. And this kind of repeats. This is helpful if you're working out any trigonometric equations as well when you go to A level, further maths, and so on. So this is 1 minus 1 here. Another one you could use is y is cosine x, and it's the exact same shape. But start at 1. So like this. So this is our y-axis. Let's say 1 is here, minus 1 is here. So it starts at 1, dips, and goes back up again and just repeats. Whereas tan x is a bit of a strange one. That has goes to like infinity when x is 90. What you get is like these weird lines, and it shoots back down to negative infinity. Does it again. And these just repeat again. Many of you need to go be familiar with graphs with distance or speed with time. So let's say this is a crossover with physics as well. A distance time graph would have distance on the y-axis and then time on the x-axis. So if something has a gradient like this shows a velocity. If it's flat, it's constant. If it's curving, it's accelerating. Or if it's something, let's say, flat, this is not moving. Whereas with velocity time graphs, you'll have velocity in the y-axis, and as well time on the x-axis. If you have a flat line this time, its gradient tells you the acceleration, whereas a flat line simply constant speed or velocity. If the gradient's changing, acceleration is changing. You'll need to know about sequences. For example, the arithmetic ones, these add up, increase or decrease by same number. Quadratic ones will are strange. They will have a second common difference. These can start to increase much quicker as you go along. For example, the common one could be 2, 10, actually 2, 5, 10, 17. And so, for example, this will increase by 3, this will increase by 7. This second common difference is plus 4. Whereas with geometric, we multiply or divide by the same number from term to term. For example, we could start at 5, and if we multiply by, let's say, minus 2 each time or negative 2, our next number would be negative 10. Negative 10 times negative 2 is 20. Then negative 40. Then 80, and so on. This is an example of a geometric one. Sequences, we could use the term-to-term rule. So it's dependent on the last one. For example, you could see formulas such as a sequence. So this little subscript determines the term number. The n plus 1 means next term. So let's say Sn would mean current. That could be a term-to-term rule, and the nth term rule is purely depends on position. For example, it'd be something typical like 5n minus 3. And all I have to do is substitute the term position, and then you get your value for the sequence. Now, with foundation, you need to know about intersecting lines. So with perpendicular lines, these cross at 90 degrees angles here, and the gradients multiply to minus 1. So let's say lines A and B are perpendicular. So let's say grade A has gradient minus 2. B would have a gradient Another way to do this is to take the negative reciprocal then change the sign. So it'll be 1 divided by 2, and then a negative multiplied by a negative is a positive, so it'll just be positive a half. So you can see that minus 2 times a half would be minus 1, so the gradients multiply still by minus 1. Parallel lines will have the same gradient and will ironically never intersect. For example, this line here has a gradient of 5. This also has a gradient of 5, and these are parallel. And with any intersecting lines, they'll meet at some point or coordinate, and they'll have the same values of x and y. So for example, we've got these lines here. A line with a gradient of half intersects the line y is 2x, minus 2x minus 2, when x is 3. Find the equation of the line. So if we sketch this out a bit, we got some sort of line like this. Then this intersects when x is 3. So we need to find the x coordinate when we're already given the x coordinates, so intersect. Therefore, we need to find the y coordinate. We can use this here to find the y coordinate. We basically substitute this x is 3 in. And we get the coordinate 3 minus 8. The equation that we're trying to find has a gradient of half. So we write down like a little template. So y equals half x plus c. And we substitute this into this equation. So we have the y coordinate 8, negative 8 equals a half times 3 plus c. C would be equal to 3 over 2 plus 8. So if we add 8 to both sides, actually, this might not be right. If we take off 1 half times 3, so c is minus 9.5. Our line equation is 1 minus, so y equals 1 half x minus 9.5. We're going to continue some intersecting lines. Remember, we're going to use, actually, now for foundation, you'll need to be familiar with using some formulae. These might be some unfamiliar ones, and you might need to convert some units. For example, the volume of a torus, which is like a little donut shape. And you'll often be given values such as its little radius here. Let's call this capital R 10 and the little r 4. Let's work this out together. So we'd substitute in our values. So 2 pi times, since there's nothing in between, so you times, multiply them together. At the end, if you do all the working out, you'll get 160 pi squared. Next we have identities which are for higher tier. Now what do we mean by an expression for a start? An expression is some letters and numbers. And it's not set equal to anything. Whereas an equation is the same, but set equal. An example of an expression could just be, let's say, half x plus 3. An equation would have to be like this expression, half x plus 3. We'd have to set it equal to, let's say, minus x plus 1. It could equal another expression. That's still counted as an equation because, crucially, we just use an equal sign. Now, an identity is like an equation, but it just works out to be like identical, basically. So no matter what the values are substituted, both are equal. And a good example of a simple identity is x plus x is identical to 2x. Because you just simplify them together, you'd collect the 2x's, and that becomes 2x on the left-hand side. So a practice question could be to find the values of a and b so that this identity is true. Well, the method here is to manipulate each side. So we'd start, for example, with the left-hand side. We may only need to do one side in a question. So we've messed around with the left-hand side. So we get x squared plus 8x plus 16 plus a. Now we can almost see which bits almost match together. For example, this b here would match what's going before x, or the coefficient of x. That would be 8. So b, we know, is 8. And then this one right here, this number, would be equal to the rest, 16 plus a. So we can make our own little equation. 16 plus a equals 1. A equals 1 minus 16, and get negative 15. Those are our two values. Higher tier students will also need to be familiar with algebraic fractions, for example with multiplying and dividing, and it's almost like normal fractions where you might have to keep change and flip if it's dividing, and you'll just simply multiply the numerators together and the denominators together. However, you need to try and factorize because things can be cancelled out. For example, if we try and simplify this is even just dividing. If we simplify the top, or we factorize it into double bracket, we get y minus 5 and y plus 1. At the bottom we get y plus 2 and y plus 1. As we can see, the y plus 1 is on both the top and the bottom, so we can divide both the top expression and the bottom expression by y plus 1. So we just left with y minus 5 and y plus 2. So you can only cancel out if you're multiplying things. And this is in the simplest form. When you add or subtract algebraic fractions, you also need to have a common denominator. For example, with this, the common denominator could be x, then x plus 1 squared, because all you'll need to get to do from this x plus 1 to x plus 1 squared is to multiply by x plus 1. So we write down the fractions again underneath, but with the new common denominator. And we just need to figure out what to multiply each fraction by on the denominator to get from, for example, let's say x to x times x plus 1 squared. This will be multiplied by x plus 1 squared. This will be multiplied by x. It will be multiplied by just x. So if we do all this, we get 2x plus 1 squared plus 5x times x plus 1. That's two sets of brackets. It's a big mess. And we just get 3x here. If we move this on top, we can combine everything onto one big fraction. If we expand all the brackets, we get 2x squared plus 4x plus 2 from this first bit. Then we get this is actually nice. We get 5x cubed plus 5x squared. And at the end, we just get 3x. If we just tidy everything up now, so we have 5x cubed on its own. We collect all the x squared terms. Collect all the x terms together. And we just have the number on its own, and it's still divided by x and x plus 1. And we still can't simplify anything, I think. Another thing you have to do in algebra is to change the subject. For most formula, you'll have to see what happens to the letter or variable you want to make the subject and just undo the operations. For example, this formula here, we want to make t the subject of the formula. So we can see we start with t and we subtract 3 from it. Then it's all multiplied by a. Then we add positive u. What we want to do now is we go backwards and undo all these. So we first subtract u from both sides. Then we divide by a on both sides. So this cancels out the a that's attached to the bracket. So v minus u over a equals t minus 3. And the opposite of subtracting 3 is adding 3. So v minus u over a is 3 just gives t on its own. So this is what it's meant by t is the subject. So t on its own. Now, there might be some harder variations where subject appears twice even after we expand brackets. In this case, you'll have to factorize. For example, in this case, we'll try and make y the subject of this formula. So we'll expand these brackets so we have 2h plus hy. So what we do next is we gather all terms with the letter we want on one side and the rest on the other. So what we mean is we want to make y the subject, so you want to get all the terms that have y in them. So like this 3y and this hy onto the left, for example. So we'll subtract hy from both sides. So we just get 3y minus hy minus p equals 2h. We'll get everything else on the right, so that's not y. So 3y minus hy equals 2h plus p. We'll factorize y out of both terms. So we get 3 minus h. And what we can do now is we can divide by this bracket here so we get y on its own. Next, you'll need to know about inequality regions, and we'll need to sketch off the inequality region bounded by these two inequality lines here. So inequality regions first stem from lines. So we have, let's say, we need to sketch first the line y is x and y equals minus 2x plus 1. So let's sketch this out and we can be a bit bigger with our sketch. So first the line y equals x is just a straight line like this, almost at a 45-degree angle going through the origin 0, 0. And then we have the line y minus 2x plus 1, so it will go intersect the y-axis at 1, go down a bit steep like this. Now this is where the inequality signs come in. Now if we have a greater than, this would be above the line. So I'm going to shade now in orange this inequality region. So the one greater than y equals x is going to be, I'm going to shade some of it, which is going to be this region here. So everything above it. It technically goes on forever. Then I'm going to shade another region, and this time if we've got a less than or equal to, so it's below the line. I'll shade this one instead in green. So this will be below the y equals 2x line. Here we can just see in that very small bit, which I'll highlight in blue, that's where both regions intersect. So that little triangle. So where both areas overlap, it's really actually it's above this line and below this line, so it's actually extends further and includes all of this. Now we're on to Unit 3, Geometry. Now we're going to look at a few bits, and this is the overview. Now, you need to know for both tiers how to use compasses. You first need to make sure your pencil is sharp, and do that before the exam. So sharpen your pencil before the exam. Now to set your compass to a certain distance, we need to first set it at the start. So you need to push both ends inwards, so that's both arms, until they touch each other. And you need to insert your pencil in and secure it until it touches a sharp point of the compass. By what I mean is you'll have a compass such as something like this round bit that controls, and you'll have the two arms here. One bit, you'll have your pointy edge like this. Your other arm will have a little bit that's kind of angled in to have your pencil, which I'll colour in black. What you want your pencil to do is to just slot in nicely like this, so that these 2 points meet together. This is what's meant by this step right here. Then, once you've done that, you can set the compass's radius by pulling both ends outwards carefully, making sure your pencil is secured in by like a little screw, and then you use a ruler to measure the radius. What you'd then have, for example, again, these arms would instead be bent outwards. Let's say you'll have the sharp point here. This is your ruler, Then you'll have your pencil like this, and that's how you'd roughly set the distance on your compass. This is important because you need to know how to make common loci. So loci is a plural for locus. That's a set of points that satisfy a rule. For example, the same distance around a point, like this, and that would end up being a simple circle. If it's same distance from 2 points, like point A and point B, what you'd first do is set your compass more than a distance more than halfway, so you'd have little arcs like this. And this is like your little line. Another one could be the same distance from two lines or edges, which is also like bisecting an angle or splitting an angle in half, such as you'll have a flat line here and another line here. What you do first from this point is that you'll have your first set of arcs like here and here. So then you can set the compass distance to any distance you like, but it should be really long enough, but not too long. Those are your first arcs, where you swirl the compass round, keeping the sharp point at this end here. So when you're drawing arcs, then your second set of arcs would fall just in between, right here. And whereabouts they cross, like this, that's where you then draw your line. Outwards, where these two arcs meet. Another use of loci could be regions as well, and these are often areas. For example, two goats may be tied to different posts with different leashes or lengths, and let's say the region shared by both goats. For example, we've got a goat tied here and a goat tied here. We'll, for example, this goat has a leash about this long, whereas this goat has like a very long leash. And this here would be a sort of region where they can both go. It's a bit like saying they're both in reach from both goats. The next thing that's covered on both tiers are the sectors of a circle. And a sector is like a slice of a circle. So you have the two radius or radii plus an arc between them. For example, if I have a circle here, my two radii, I'll color in orange or draw in orange. And the arc I'll draw in blue, just highlighted right here. And you'll measure often an angle in between, like this. And the area, first, is basically like a proportion of the normal area of the circle. So your normal area of the circle is pi times the radius squared, but then you take a fraction of it based on the angle. So the angles on the point add up to 360, and that's just theta, that's the angle. And this is read as theta. Whereas the perimeter is you've got the arc, which is part of circumference, plus the 2 radii. So that would be the arc, would be part of the circumference. So the circumference is 2 pi r. Then you'll just have that over 360, the angle over 360. So that's like a portion of the circumference, plus the 2 radii, 2r. And don't forget this, this is most forgotten. Next are the parts of a circle. I've got 8 parts of a circle, which I'll label quickly. And I'll just make out the center of the circle as here. First is the radius, which is from the center of the circle to any point on the circumference. So this is 1, the radius. The diameter is from a point on the circumference to another point of the circumference, like a straight line passing through the center, like this. The diameter equals 2 times the radius. A chord is simply put a line drawn from a point in the circumference to another. It doesn't have to pass through the center of the circle. The circumference would all be this, which I'll highlight. Then an arc, as I've just said, is a portion of the circumference, such as, and it's bound often by 2 radii. A sector is bound by 2 radii, and then an arc whereas a segment is just bound between the an arc and a segment, such as this. You may want to screenshot that. Now, the foundations here would also need to know about the basic properties of triangles. For example, angles in a triangle always add up to 180 degrees, and you have a few special types. Equilateral ones, all 3 sides equal, all 3 angles equal. 60 degrees. Isosceles ones will have 2 angles equal, 2 sides equal. This could be this, for example. So with the dash, equally long lines. And these two angles here shall highlight are the same. The next one is a scalene triangle, which is basically nothing equal. The last one is a right angled triangle, so where one of the angles is just 90 degrees. This is often used for Pythagoras. You also need to know about translations. For example, quadrats can be written like this in the form x plus x then y as simple commas, but they can be written vertically as well. So the x value on the top, the y value on the bottom. And you'll often have brackets around it like this. Transformations can be described in, let's say, a few units up, a few units left, and they can be written vertically like vectors. So transformations basically add something to a coordinate. So the top number is how far right it goes. And the bottom number is how far up vertically it goes. For example, let's say 0.36. So this transformation here would be 1 to the right and 2 down. And that would be from 3.6. And this could be like a little sketch there. Congruence is something for higher tier, and then this proves that two shapes are exactly the same. So sides between them are the same, all the angles are the same, even though they might be rotated slightly. There are proofs for two congruent triangles. For example, if you have the same three sides, two sides and an angle between them, two angles and a side between them. Two angles and a side attached to the same angle. For example, if I had angle A, angle B, then a side length of, let's say, 2, you can see that this angle A is opposite to the numbered side. Then this numbered side is also attaches to angle B. So if I draw it differently, like 2 here, then angle A, then B, this would be AAS, congruent. Another one could be two sides and an angle between them. And then the last one would be hypotenuse and one side length in a right angled triangle. This is because of Pythagoras. Higher tier would also need to be familiar with prisms and volume. So a prism is a tube, so where its cross section is the same throughout. So think of things like cylinders are a good example. Cubes are also prisms. So if you could take a straight cut through them, it would have the same shape throughout. An example even could be just a weird shape like this. where this is the cross section, and this right here would be the length. And its volume is equal to its cross section times the length. Now, a hard topic for higher tier is exact trigonometric values, which everyone struggles with. As prior knowledge, you'll absolutely need to know about SOHCAHTOA. You need to remember SOHCAHTOA. Because in the time you forget in the exam, you may need to go back to this. So method 1 is drawing out the triangles. One of the triangles would be one with 45 degrees angles. Remembering that the two sides are equal, since this is technically isosceles. And if you do it with Pythagoras, you'll see that this hypotenuse is root 2. And we can see a few things. For example, sine 45, cos 45, and tan 45. So sine 45, this would be opposite if we just ignore one of the angles. We'd have opposites followed by hypotenuse. This. So you do 1 divided by square root of 2, you'd rationalise this, this becomes root 2 over 2. Cos 45 happens to be the same, 1 divided by root 2 over 2. Tan 45 is opposite divided by adjacent, so it'd be 1 divided by 1 is just 1. The other angle you'll need to remember has a hypotenuse of 2, a short one of 1, and the height of root 3. This actually comes from the equilateral triangle. So it's where we split the equilateral triangle in half. So let's say we have an equilateral triangle, 60 degrees, side length of 2, and we split it down the middle. We've got a right angle here, and we know angles in a triangle add up to 180. So 180 minus 90 minus 60 gives you 30 degrees. And if we do, this gets split into half, so this is 1. If you do a bit of Pythagoras, this is height is root 3. And that's why we just concentrate on this angle here. So we've got 30 degrees at the top and 60 down here. Then we can see a few values. Now, for example, sine 30, cos 30, tan 30, and then sine 60, cos 60, and tan 60. I'll just write down the values here. So we'll start with 30 degrees. So this would be opposite, this would be adjacent, this would be hypotenuse. Sine 30 is a half, cos 30 is root 3 over 2. Tan 30 is 1 divided by root 3. So that's root 3 over 3. We'll erase those again, and we'll do it for 60 degrees. So this would be adjacent, hypotenuse still, and then opposite. So sine 60 now is root 3 over 2. Cos 60 would be a half. Then tan 60 over a would be just root 3 over 1, or just root 3. But this doesn't solve the issues for 0 and 90 degrees. This could be helped really if you know the graphs of each. The other method is using your hand, and you'll have to apply few rules. So if I draw out your hand, so you have your thumb, finger first, second, third, and the last one there. Sine of the angle would be fingers below divided by 2, so your bottom finger is 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees at the top. So the angle you want, you fold it in. So angle, and those are your three formulas. So for example, with sine 0, you'll have the square root of the fingers below, which are none, divided by 2. So sine 0 is 0. With sine 90, you take the top finger away. So that'll be the number of fingers below. So there's 4 of them. The square root of that is the square root of 4, so 2. And that's divided by 2, so we get 1. Cos 0 would be the fingers above, so we put away the bottom finger or the pinky, count the number of fingers above, which is 4, so the square root of 4 is 2, and that gets divided by 2, so cos 0 is 1. Cos 90 is, you remove the top finger, fingers above, none, so that's 0. Now tan 0 would be fingers below, we'd remove that. So 0 divided by 2 is just 0. Tan 90 would be, however, fingers below, which is square root of 4 divided by square root of fingers above, which is that 0. So you get 2 divided by 0. So actually tan 90 doesn't exist, or is indefinite. Because if you remember on the graph, that sprung up to infinity and then restarted in negative infinity. And a useful fact is, if you can't remember this weird tan rule, you could still remember that tan of an angle equals sine of the angle divided by cos of the angle. That's an identity. That's just a fact. And you may need to know, use these values beyond 90 degrees. So if we need to, we've actually seen sketches of these already. For example, sine x is one of the easiest to remember. It's just like one of those waves. So it repeats every 360 degrees. That's with any. So we got the peak, if you remember, at 1, at 90, 0 at 180, negative peak at 270, and then to 0 at 360. Cos is just the sine wave, except it starts at 0 and at 1. By what I mean is, goes more like this. So it's like the sine wave just shifted to the left. And the tan, y equals tan x, flicks up to infinity at 90, and restarts again at negative infinity. It goes up again, flicks up to infinity again at 270, crosses 0 at when the angle is 0 and 180. And 360. And it may be useful, for example, if you're solving trigonometric equations as well, because you can draw lines that intercept. The only thing I can think of is you could use obtuse angles. For example, they could ask you for sine 150. And what happens is, for example, with sine, it's the same process from um hmm, so do you keep it like it's a half. So it's like a half here. 3/2 here, you peak at 1, and it goes to root 3/2 again. So as an extra note, sine 150 would be wait, that'll be 1/2. Sine 120 is root 3/2. Because it can kind of go curves a bit. It's symmetrical, if you like, after the peak. Now we're on to the final unit tonight. This is statistics and probability. Here's an overview. I might have taken a few things out. And we'll start with Venn diagrams for both tiers. Now this symbol means all data, all the set. This could be a group of numbers, some different cars perhaps, and then you've got notation of terms such as intersection and union. So intersection is where like there's both groups, like it's in both groups like an and union is more like an or, so it includes both groups. For example, in a sixth form college, there are 150 students, 55 study biology, 48 study chemistry, and 78 do not study either of these subjects. Now you've got to take into account that both of these basically include like the intersection. So if we draw this in a Venn diagram, so we'll have biology on the left, chemistry on the right. So you've got 150 students in total. 78 don't study either. Right. So we've got 78 that don't study either of these subjects. Then we have 150 minus 78. 72 people that study, these study just biology. just chemistry or both? Because if we just count this biology, so that includes the overlap, and the chemistry also includes the overlap, so it overlaps kind of twice. So there's a rule for this. So if we solve this, we get 90, 13. So in the middle, so those who study biology and chemistry, there are 25 of them. So if you subtract these from the biology and the chemistry total, we'll just get the numbers that do, for example, biology only. That would be 30. And then 23 here. And to check, hang on, 72. There's actually only it's a mistake. 72, 31. Yeah, there's only 31 that study both. So that means there's 17 that study chemistry only. And there's 24 that study biology only. So if we add them up on as to check, you get 150. Next, we'll calculate the probability of B union C. So basically this is all the students that are in group B or C. So they can be in just B, just C, or both. And that's what it is right here. And it was 72. So that's 72 out of the 150 students. Just 12 over 25. Now you'll need to know about some probability keywords, and these may come up in questions. For example, A and B are independent. And we'll start with that one. First, independent means these are events that don't affect each other. So they'll happen by coincidence, for example. For example, this could be flipping a coin once, and then flipping a coin again. Those two events, like flipping the coin before and after, won't affect each other. Dependent ones often are events that affect each other. For example, a common example would be picking an object like a sweet out of a bag, not replacing it, and then picking another one, because the total number of sweets has changed, so the probabilities have changed. If an event or multiple events are exhaustive, at least one event will happen. For example, when you roll a dice, the probability of you um, rolling an odd or an even, that's an exhaustive combination. And then a mutually exclusive means that the events never happen together. For example, you can't be late and not late at the same time. When you roll a dice, you can't have an even and an odd number at the same time. For foundation, you'll need to know about two-way tables. So there's this girl, let's say Janice, and who asks 100 students if they like biology, chemistry, or physics best. 38 of the students are girls. 20 of these girls like biology best. 18 boys like physics best. 7 out of the 23 students who like chemistry best are girls. And we need to work out the number of students who would like biology best. So we need to draw a little table ourselves. So we'll do in the top biology, which is a B, chemistry, C, physics is a P, and then we'll do the boys, and then the girls. And don't forget you'll need total columns as well. We'll put down the information. So in total there are 38 students who are girls. 28 of these girls like the biology test, or like biology best. 18 of the boys like the physics best. And 7 out of the 23 students who like chemistry. So there are 23 students who like chemistry overall are girls. So 7 here. And the total here is 150. For example, total of 23 would be this column plus this column here. So we could do 23 minus 7, we'd get 16. So there's 16 boys and 7 girls who like chemistry to make a total of 23. We've got the number of girls, so 21 girls plus 7 plus another number of girls who like physics best, make a total of 38. That would be 10. Then we can infer from that the number of people who like physics best would be 28. Since there's 38 girls and the rest are boys, there would be, well, 112. This leaves it quite lopsided. So for some reason, there are 78 boys who like biology best. Therefore, overall, there's 99 who like biology best. So that's our answer there. And remember, you don't always need to fill in the whole table. Next for foundation is the types of averages and maybe outliers. Now there are 3 ways to calculate an average. First is the mean, and the mean is, well, quite nasty to us because we have to calculate it. If you like, this is the sum of all numbers, like all the data, divided by how many numbers there are. As the median is the middle item in the list when in order, And the mode is just the most frequent. Now, here's a bit of discussion. Which average is better? Pause this video if you like and try and figure it out. So first, I would say the mode is the worst kind of average, but it's best when it's dealing with non-numeric data, like colors, because means and medians can't do much there. It's not quantified. However, it's quite useless, I'd say, because sometimes it doesn't exist. Because, for example, if a number appears once, or all of the numbers appear once, the mode doesn't exist because nothing is the most frequently found. At the other end, I'd say the mean is the most useful because it uses all the data. However, it can be greatly affected by outliers. For example, let's say we have the list 4, 8, 18, 50. We can see the 50 is an outlier. So if we calculate the mean for this, it would turn out as 20, whereas the median would be 13. The mean isn't as representative because it's affected by this large number, which kind of bumps it up, if you like. So this is larger than 3 of the numbers there. It doesn't make sense to be the middle of the data. Whereas the median, therefore, it's not affected by outliers. But it doesn't use all the data. Next, for higher tier, you'll need to be familiar with cumulative frequency. So let's say we have some data here in the table. And usually you'd have some classes with an inequality. So if I write m for each, you'd have an inequality sign. So the lower bound is often less than or equal to like this. And this makes sure the classes include the data but don't overlap. You'll often find an empty column here. This would be labeled as cumulative So basically we'd add these up as we go along. So we'd first start at 12, then go to 34, then 55, then 70, then 83, then hang on, 12, 34. I think this is 80. And then you'd be asked to plot a curve. But the thing is, you'll need to have like an end, use the end point. So if I erase some of it, I'll just write cumulative frequency as CF. Hmm. So this first cumulative frequency includes the data from the first class. So how many students scored up to 10 marks? So then the next cumulative frequency would also include those who scored from 10 to 20 marks. So overall, it's those who scored less than 20 marks. Next is those who scored less than 30 and 40 and so on. Now what you'd get is either a little dot to dot curve like this, or if it asks for a curve, you may have to draw a smooth curve which will pretty much look similar anyway. And then you'd use this to estimate things like the median, interquartile range, and a common question would be to this is why your answers to A and B are estimates. And here's the data again. So the median is the middle position of the data. So since there are 100 pieces of data by the total frequency of 100, we draw a line going to first 50. Then what you try and do is rule down. And you try and estimate it from this axis. And that would be, I'd say, something like 28. That's the median. The interquartile range would be the middle 50%. So that's like where the marker for the 25%, then the 75% of like the frequency. So in this case, it's quite easy since there's 100 pieces of data or a total frequency of 100. So you'd read off from 25 and 75 down to the x-axis, then find the difference between the two. So I'd first draw my line at 25, frequency of 25 to the line. Then draw down, and I'd estimate that to be around 16. Then do the same but at 75, then down. And that would be around, let's say, 37. So interquartile range, 37 minus 16, that would be 21. And the reason why this is an estimate is because the data is grouped. We no longer have the exact values. Next is a tree diagrams. And these can have a few variations. Like two of them would be with independent events, and these would come in the form if something is replaced or not replaced. Example could be there are 8 sweets in a bag, which are red or yellow. 3 sweets are red, and I take out, let's say, a red, eat it, then take out yellow. And then you calculate this probability. And a famous question from 2015 was this question involving Hannah's N sweets. So this is from the Edexcel. Now there are N sweets in a bag. 6 are orange, the rest are yellow. Hannah takes a sweet at random from the bag and then eats it. Then Hannah takes another sweet at random from the bag. Now we're told the probability that Hannah eats 2 orange sweets is 1/3. And then suddenly the question says, show that n squared minus n minus 90 equals 0. So what we do is first draw a tree diagram. So we draw a branch going to orange and the one going to yellow. So then we know the probability of something happening is what we want to happen, so decide divided by the total trials. So that would be like how many sweets that we want to pick out divided by how many in total there are. So probability at the first pick of picking an orange sweet would be 6 divided by the n sweets in the bag. And we don't need to worry about the yellow. And then if we pick another orange one, there's now 5 sweets because Hannah just ate one. But also the number of sweets is decreased by 1. So there's n minus 1 sweets. You need to know that the probability of both 2 events happening is like an and, so we multiply them together. So we know this probability is equal to 1/3. And all we got to do is just solve this equation. So first we multiply both sides by 3 for now. Or we just tidy up the fractions, we get 30. If we multiply both sides by 3, we get if we multiply both sides by this denominator, we get 90 equals n minus 1. Expand the brackets, we get 90 equals n squared minus n. And if you rearrange this, we finally get n squared, so if we subtract 90 from both sides, minus n minus 90 equals 0. That's it. The penultimate thing we're doing now is independent events, which is a link to Venn diagrams. So independent events, if you remember, for something happening both together, for 2 events happening at the same time is an and that's simply by coincidence. So that would be probability of A happening times the probability of B happening. An OR rule would be, so that'd be either or both. But if we just have probability of A happening and the probability of B, remember you had like a little overlap in the Venn diagram as well. For example, if we have 2 again, so if we have A here, we draw another diagram. We have B here. If we shade in B, we can see that this intersection counted twice. So we need to subtract, so what it really is probability of A plus the probability of B. We take away one lot of that intersection, so probability of A and B. And this dash just means of it not happening. And these are mutually exclusive, so that's just 1 minus the event happening. Because you have an event happening plus not happening is equal to 1. Last is expected value. So this is where we can test if something is biased or not. So if we roll the dice, let's say 50 times, how many times would each number come up? So we would have each outcome, let's say 1 to 6. We'd have, let's say, frequency. So expected value or frequency is number of wanted outcomes. That could be, for example, you want a certain number, or you want, let's say, an even number divided by total outcomes times the number of trials. For example, you'd expect a 3 to come up 1/6 of the time. So for example, which is just about 8 times. However, it can be higher or lower than expected. It could suggest it's biased. However, you could test more, and then the probabilities or frequencies even out. And that's it for the PowerPoint. I hope you enjoyed this lesson, even though it's quite a long one. I'll see you soon.